All right, that was a bit of a scary trend line. Let's continue this interpretation. You can do what I just did in R, also in Excel. Just fitting a simple linear trend line. So I'm going to do a similar thing just to help you understand this data presentation. Again, I'm showing you annual deviations of temperature against this base period. So the 0 is the base, and positive is a higher recorded temperature, and a negative is a lower recorded temperature against that base period. I've now taken data for the southern hemisphere, since that's where Australia is in. And instead of a graph with just crosses, I'm showing you a bar graph. So we can fit a trend line, which is showing that, yes, on average, temperature is going up. In fact, it's going up with 0.086 degrees per year. Remember, this is the slope of the trend line. And to test whether that is indeed a significant increase, you can look at the p-value of that coefficient if you were to estimate a linear model. But is that straight line indeed a correct line? I can look at the r² value, which shows that this model has an 83% correct prediction. But maybe a curvy line would fit better. Yes, indeed. This is a curvy line that I've estimated, an exponential function. And if you look at the r² value, it's higher than the linear model, which tells us that this curvy model, this exponential model, fits the data better. What does that tell you? Does that trouble you? I would say a curvy line is scarier than a straight line because it means that the temperature is going up and up and up and up faster and faster, which indicates trouble in the future. Now, what other data? You could also look at maybe averages every 10 years. I've here just taken a 10-year average, fitted that line in Excel, and you can see again that the averages are increasing over time. Now, some people have argued that, right, 160 years of data, that's not enough. The Earth has gone through colder and warmer periods for centuries. And this data that you're showing us here isn't proving anything. So what I've done is I've looked at a longer time scale. I'm again showing you temperature deviations, but this time not from the 1880s, but from the year 200. So nearly 2000 years of data, with the 0 as the average over a base period, and again all the deviations. And this data has been collected through ice cores reconstruction. So what this is showing us, that the world has been colder all throughout that record of nearly 2000 years, except for the past 50 years. So when this data first came out in the 1980s, it was known as the hockey stick. Oh, bit straight, and then suddenly, oops, going up. Very scary observation. There really is increasing evidence that the temperatures are changing and that they're increasing. I wanted to show you this cool graph because it again shows changes in temperature, in this case for a little bit of a difference reference value 1950 to 1980. And they looked at summer temperatures. These authors published a paper in PNAS. You can find this on the website. And what they've done is they looked at average temperatures and the distribution of those temperatures. And they displayed them as a normal distribution for different decades. So the reference value is 1950 to 1980. And I'm just showing you 3 decades for reference. The first one is 1950 to 1960, 1980 to 1990, and then 2000 to 2011. 0 is the average for that reference period. And the peak is the average for that time period that is being shown. So what are you seeing here? What is this graph telling you about the average temperature? Well, first of all, you can see that the average temperature is moving to the right, which means that the temperature is increasing for those decades. What do you see in the distribution of temperature? Is it growing wider or more narrow? It's growing wider over time. That means that there is increased variability in temperature. And because it's a normal distribution, this seems to be going down, but that's an effect of the distribution. Now let's look at the deviations for each individual decade. They also plotted as a normal distribution. So it's the same information, just presented a little bit differently. You see here is the average, that's the base period. The positive here is a little bit warmer, this is a little bit colder, but on average it's a normal distribution. Now if we look at these last 3 decades, 1980, 1990s and the 2000s, you can see that it's slowly moving to the right. More and more of that deviation in a higher, warmer quadrant. So first of all, this graph is showing you that the peak is moving to the right, which means that average temperature is increasing. And second, you see that the graph is getting flatter and flatter, which means a bigger standard deviation and a wider spread of the results. So more variability in temperature. Now, let's say that we believe all this science. Then there's still the question of whether we should do something about it. Because it may be very expensive to undertake action to avoid climate change. But then on the other hand, not doing anything may also be very expensive because of all the climate change impacts. And that's exactly what I'm going to talk about in the next lecture. How do we decide whether to take action? While you have another break, I'm going to show you another cool visualization of changes in global temperature. Let's see if that works. You can also click on it at home. There we go. So you see that temperatures are getting wider and wider, which means they're getting higher and higher. These are global temperatures, so not per country. Can we run that again? There we go. Still pretty good. Oh, and then in the 1940s, we're getting higher and higher. It's just scary to look at. Oh well, have a break. I'll be right back.